Hi everyone, this is Mike with a brief video about derivatives in order to give you an overview about what to expect in Module 3 if you are previewing Module 3. And if you're reviewing Module 3, my hope is this will give you a good summary of what you've been working on. This is the second video in my series that I'm calling Calculus in a Nutshell. And my hope is that it gives you kind of a big picture idea of how to think about important ideas in calculus. So remember that calculus is really about three primary topics or concepts. Module 2, which is about limits. And in the first nutshell video, I tried to convince you that limits were actually the only topic in calculus. And if you're looking at this video after working through Module 3, my hope is that you have a good sense of why limits are related directly to derivatives. But although limits really are a thread that run through the entire course, it's fair to say that derivatives are a topic unto themselves in Modules 3 and 4. And the same will be true for integrals in modules 5 and 6. One thing to keep in mind, derivatives are rates of change. And a shorthand way of thinking about a rate of change is to think about it as a slope. Now, calling it a slope might be a bit too narrow, but I think as a short description of what derivatives are, I think it is valid and useful. Derivatives really are just rates of change, instantaneous rates of change. And when we think about rates of change, most of the time, the first way we encounter that is with slopes. Now, derivatives are slopes, but derivatives are also limits. So what does that mean? Well, the idea, if you remember back at the beginning of Module 2, you were looking at slopes of secant lines and thinking about how those slopes of secant lines created a pattern and gave you an indication about what the slope of a tangent line might be if the 2 points connecting the secant line got closer and closer together. So the idea for a derivative is that the derivative is the limit of the slopes of those secant lines as those 2 points get closer and closer together. And so the secant lines represent average rates of change, whereas the slope of the tangent line represents an instantaneous rate of change. So in algebra, you do average rates of change, you do slopes of secant lines. And in calculus, we're focused on instantaneous rates of change. And the way you make the leap from one to the other, the way you connect average rates of change to instantaneous rates of change, is to think about limits. And that's how limits play into the process. So we have this fancy formula for the derivative of f, otherwise known as f prime of x. And this fancy looking formula is really no more than the slope formula with a limit attached to it. If you think about what this formula looks like, take the f of x plus h. Well, that's a y value, and we're subtracting another y value, f of x. So that's really what you do in the slope calculation. You take a y value and you subtract another y value. The x plus h component just indicates that we are talking about a point that is different from x. So we're looking at the y value at x, that's what f of x represents. And we're also looking at the y value at x plus h, which is a slightly different value. And then likewise, we look at the denominator of that, and we take the two x values, namely x plus h and x, and we subtract those. That's exactly what you do in the slope formula calculation. You take the two x values and you subtract them. And comparing the change in y with the change in x is what gives you that slope m. So when you look at this funky formula for the derivative, you really want to be thinking about it. I recommend that you think about it in terms of a slope. So the y values are on top and the x values are on the bottom. And then the derivative which is more than a slope of a secant line, which is what this part of the formula indicates. This is the slope of a secant line. But the limit describes what happens as the 2 points get closer and closer together. That is, the h that we're changing the x value by goes down to 0. So the limit as these points get closer and closer together is going to give us the instantaneous rate of change, which is also the slope of the tangent line. And that's why the derivative is really just a slope. So let's go back to just remind ourselves what's going on and think more broadly about, or maybe a little bit more specifically about what's happening in Module 3. So in Section 3.1, there's a basic definition for derivatives where you really talk about how derivatives are related to the instantaneous rate of change and thinking about how that relates to the slope formula and how we take a limit of that slope formula to get the derivative of a function. But Section 3.2 takes us a little more deep into the concept to say that we can actually create functions out of that. That at every point on a curve, every point on a function, there is a slope of a tangent line. And so there's a slope that corresponds to every point, and that makes the derivative of function itself. And so just like other kinds of functions, derivatives have algebraic formulas, they have graphs, and we can create tables out of them. Section 3.3 summarizes most of the important differentiation rules. Differentiation is another way to say take the derivative. So the idea of being able to use those rules will be to use those rules in different representations. So there are formulas for sums and differences. There are formulas for multiplications or products. There is a formula for the quotient of two functions. And there are also formulas related to trig functions. Section 3.4 gives us another differentiation formula, which is called the chain rule, and the chain rule applies to functions that are inside of other functions. In other words, the chain rule applies to composite functions. And one way to summarize that rule is simply to say that we're going to differentiate the outer function, leaving the inner function alone, and then we're going to multiply by the derivative of that inner function. And again, if you're watching this before embarking on Module 3, there will be details describing why that is the way that works. And if you are watching this video at the end after having completed Module 3, my hope is that you are able to describe for yourself where that comes from. Related to the chain rule gives us implicit differentiation. So that's a different but very closely related technique. Just a few tips to keep in mind for Module 3, again, whether you're at the beginning or whether you're at the end. My recommendation to you is to challenge yourself to think about derivatives as more than just plug-and-play formulas. How does the graph of a derivative relate to its parent function? How can you think about a derivative in ways that takes you beyond just an algorithm or a series of steps to sort of blindly follow? The deeper you can challenge yourself in thinking about derivatives, I think the stronger your understanding will be. My hope is that the assignments and the activities will help you challenge yourself in those ways. But if you're looking for additional ways to challenge yourself like that, once you finish the assignments and activities, then I recommend going back to the textbook and trying some of those exercises at the end of each section. And particularly, I'd recommend focusing on questions and items that involve working with derivatives in the context of tables and graphs that sort of get away from the algorithmic or formula-based ways of working with derivatives. And again, I think that can help you deepen your understanding and prepare you better for the units ahead and being able to use derivatives as they're intended. So I hope that is a helpful summary of Module 3. As always, let me know if you have questions.